Hello everyone, my name is Michael Oliver, and the project I worked on under Bernardita Salato this summer was geospatial tools for smarter agriculture by using Mergin maps and QGIS for crop classification. First, I would like to give a brief background of myself and my experience with AgAid. I am an undergraduate in computer science at WSU and was an AgAid intern back in 2022 under Matthew Whiting, where I had such a good experience that I continued to work at WSU IREC for the continuing summers, and this year I am an AgAid intern once again. Finally, back in January 2023, I competed in the AgAid Agathon, which was a 48-hour competition to use AI methods to solve agricultural problems, and my team and I got first place in the labor division. As for this project, it explores how geospatial tools and machine learning can support agricultural research, particularly in orchards and vineyards. For crops like apples, cherries, and other perennial crops dominant in Washington state, it's critical to monitor characteristics such as crop type, growth stage, and planting system, not just for record keeping, but to study how these factors affect the yield, the health, and even the management practices. By combining mobile data collection through the Mergin Maps mobile app with the QGIS desktop system, which stands for Quantum Geographical Information System, we've created a streamlined way to collect and visualize this data within a spatial context. From a research perspective, one major barrier is scalability. That being manually identifying and labeling crops takes a significant time and expertise when the data set is very large. And machine learning offers a path forward by automating this process, which allows researchers to analyze larger data sets more efficiently. In turn, these research insights can help inform farming practices, improve decision making, and ultimately benefit growers on the ground. As for the data, it was collected in field using the Mergin Maps mobile app, which allows for GPS tag sampling. At each point, we recorded detailed information, that being what type of crop it was, how it was trained, its maturity stage, and any notes or photos as needed. Once collected, this data was then synced with QGIS on the desktop, where we can then visualize it on a map and begin to process it. In QGIS, we prepared the data for use in machine learning by labeling areas based on the previously mentioned attributes and ensuring attribute fields were clean and standardized. As for the training data, I first want to make sure that we all have a quick understanding of machine learning, which essentially enables computers to recognize patterns by training on examples, just like how we learn to identify things by seeing many examples. In this project, we used a YOLO, you only look once model, which is optimized for object detection in images. It's ideal for identifying things like trees, trellises, or crop systems in the aerial photos that we collected. And during training, we provided the model with labeled images, essentially saying this is a freestanding mature tree and this is a vertical hop orchard, and so on. The model then looks at pixel patterns and begins to form internal rules about what features correspond to what labels. And once trained and validated, the model can then predict labels on new unlabeled images. Of course, the accuracy of this does depend heavily on the quality and quantity of training data, which was somewhat difficult to work with during this project. When training the data, we had around 350 pieces that we used for the input, that data being the input plots of the areas that we mapped on QGIS. I placed two key graphs from the results on the right side. The first one on the left being the precision score, which tells us how many of the model's predictions were correct. We can see peaks after a while before dropping, which tells us that the model was sometimes overly confident and not always correct in its assumptions. The mean average precision score on the right measures how well the model finds and correctly draws boxes around the objects in the image, which, as we can see, also peaks before dropping, telling us that it was best at identifying and locating orchards early on in training, but it began to forget or overfit. As for visualizing the output images, this is one aspect we need to improve, as the current output appears black, likely due to the satellite image colors not being scaled properly, so the differences between light and dark areas aren't showing up clearly. As such, one limitation for this project was the difficult visual output, which we are currently working on. Additionally, when training first began, the program kept crashing as I was doing it on my laptop, which wasn't powerful enough, so I had to move operations over to my desktop. As for the future, I plan to improve the pre-processing step to include higher quality images, as well as collect additional data through Mergin maps with help from the Salado team. The image on the right, we can see it's an image of the Yakima Valley. The data points I collected were mainly in the lower portion, so we still have a reasonable area to cover. Finally, I would like to thank everybody a part of the Salado team. I had a great time working with them all this summer. I would also like to thank Martin Churrovija for introducing me to and assisting me with this project. And of course, I would like to thank AgAid for having me back again this summer. Thank you. Hello, everyone.